Good day to all. Today I am going to present our paper, four-quadrant operation of bi-directional DC-DC converter for light electric vehicles. Myself, Carolyn and Sam. I am from Department of Electrical and Electronics Engineering, Research Scholar, Karuni Institute of Technology and Sciences, Tamil Nadu. My co-author is Dr. V. Jegathesan, Associate Professor, Department of Robotics Engineering, Karuni Institute of Technology and Sciences, Tamil Nadu, India. These are the table of contents. Introduction, bidirectional DC-DC converters for EV, working principle of the bidirectional full bridge DC-DC converter, simulation studies of bidirectional full bridge DC-DC converter for BLDC drive, hardware demonstration of bidirectional full bridge DC-DC converter, results and discussion, conclusion and acknowledgement. Now, electric vehicles are gaining attention nowadays due to their attractive features like noiseless and pollution-free environment. Now, widespread research is happening in the field of EV drivetrain to improve the overall vehicle performance. Now, EV drivetrain basically consists of an energy source, photonic converters, and electric motors to drive the vehicle. Photonic converters basically consist of DC-DC converters and inverters. Among these, DC-DC converters play a vital role in controlling the power flow from the source to the inverter, and if we provide bidirectional converters, it will aid bidirectional power flow from the source to load and vice versa. Now, for EV, bidirectional DC-DC converters are used for aiding the four-quadrant operation of the drive, which improve the overall efficiency of the drive. Now, in four-quadrant operation, braking energy is utilized to charge the vehicle battery. Now, this braking energy is utilized in quadrant 2 and quadrant 4 operations, reverse braking and forward braking operations. Now, basic working of a bidirectional DC-DC converter is similar to that of a conventional unidirectional converters. The only difference is that we are providing a path for the bidirectional power flow. Now, in the proposed converter aids in both buck and boost mode of operation, which helps in improving the vehicle performance effectively. Now, coming to the working principle of the proposed converter, we have designed a 2 kilowatt bidirectional DC-DC converter for input voltage range of 12 to 60 volt range, and output voltage again it has a range of 12 to 60 volt. Switching frequency is 25 kilohertz. Now, since it is a buck boost converter, the relation between output voltage and input voltage is V out equal to V in into D by 1 minus T. Now, V in is 12 volt, V out is 60 volt, and duty ratio obtained is 0.833. Now, assuming the resistance to be 100 ohm, then the minimum value of inductance obtained is 0.05 millihenry, and the input and output capacitance are obtained as 470 microfarad. Now, this is how we design the converter. Now, there are basically 4 modes of operation for this converter: forward buck mode, forward boost mode, reverse buck mode, and reverse boost mode. In forward operation, the power flows from the source to load. In both, in this mode, we get both buck and boost mode of operation. If the reference voltage is less than the actual output voltage, we have to operate the converter in buck mode. If the reference voltage is greater than the output voltage, actual output voltage, we have to operate the converter in boost mode. Now in reverse buck and boost mode, the power flow direction will be reversed. Otherwise, the operation is same as that of forward mode of operation. Now let's see each mode in detail. In forward buck mode of operation, we are turning on switch T1. So the current flows as shown in figure A. Now we turn on T1. So the freewheeling action happens to D3 and D2. So this A and B together gives you buck mode of operation. Since the power flows from source to load, we are mentioning it as forward operation. In boost mode of operation, that is figure C and figure D, initially we turn on switch T1 and T4. So it will charge the inductor. Then we turn off switch T4. So the energy stored in the inductor plus the supply energy will be given to the load. So this helps in boost mode of operation. Okay. Now in the reverse mode of operation, power flows from load to source. Figure E and F demonstrates buck mode of operation. Figure G and H provides or demonstrates boost mode of operation. Now this shows a flow chart shows the control strategy for bidirectional DC-DC converter. Here, initially we have to select the mode of operation. Then, depending upon the direction, we have to select the switching strategy. Okay. Now, if the speed error is positive, we'll load the sequence table for forward motoring. The speed error is negative, we load the sequence table for forward braking in the forward direction. If the direction chosen is reverse, and again we check for the speed error. If it is positive, you load the sequence table for reverse motoring. If the speed error is negative, you go for reverse braking. Now, if the reference voltage is less than the input voltage, we have to operate the converter in buck mode. If it is greater, we have to operate the converter in boost mode. So accordingly, we have to choose the switching strategy. Now the figure shows the simulation diagram of a bidirectional DC-DC converter. Now we have connected the converter to a BLDC drive, which is used in EV. Now here, this shows the full bridge bidirectional DC-DC converter. This is the three-phase inverter of the BLDC drive. Now this is the Hall sensor switching, Hall sensor load sequence generator. And now here we have generating the gate pulse for the inverter. Now the reference speed given is 2000 RPM. Here you can select the direction, whether you are going for forward operation or reverse operation. Here you can select the motoring or braking operation. So these two will decide the mode of operation. Either you have to go for forward buck, forward boost, reverse buck, or reverse boost. Now here, if the voltage corresponding to the reference speed is greater than the actual voltage, converter operates in boost mode and vice versa. Now in this simulation, a voltage of 51.66 volt corresponds to a speed of 3154 RPM. Switching pulses are generated using outer speed control loop and inner current control loop. Now this diagram shows the hardware setup of the used converter. We have a bidirectional full bridge DC-DC converter. The control pulse is generating using C2000 launchpad. This is the 30 volt DC supply used, variable DC supply. We are testing the converter with a resistive load. Output voltage is monitored using multimeter, and same switching pulses are monitored in the DSP. MOSFETs use a P80NF10. This is the control algorithm which is dumped in C2000 launchpad. Actually, we are working in a MATLAB-DSP integrated environment. So in MATLAB Simulink, we are using this Simulink diagram. ADC pin corresponding to the C2000 launchpad serial number is loaded, is used. EPWM pulses or EPWM blocks are also used corresponding to the controller which we are using, F2837. Then from the ADC pin, we get the actual load voltage. Using proper scale, we are comparing it with the reference value. The error is given to a PI controller, and that is given as the DC pulse for the DC signal for the EPWM generation. So each EPWM block will generate two pulses, one for S1, T1, T2, and second for T3, T4. Now about the results and discussion, these are the simulation results which we obtained. In forward buck boost, according to a speed of 1000 RPM, we got 1190. These are the corresponding input and output voltages. For forward boost board, we got 1500 RPM. For a reference speed of 1500 RPM, we got 1505 as the actual speed. Then reverse buck and reverse boost mode also. Then these are the output waveforms obtained. The first diagram shows the speed of the real AC drive. Initially, we are giving a reference speed of 2000 RPM. So, speed gradually increases. It reaches a maximum value. Then we are giving a braking mode of operation. So the speed reduces. Then again, we are giving a motoring mode. So in this way, in the braking mode, if you notice, the SOC have slightly increased. The expanded view is shown in figure B. SOC mode has slightly increased. These are the hardware results obtained. Forward buck mode, for reference speed of 24 volt, we are getting 24.5, and for other modes of operation also. Now, conclusion, we have demonstrated the closed loop control of bidirectional DC converter. Converter is implemented on onboard chargers. Four-quadrant operation is demonstrated using MATLAB Simulink software, and a prototype 2 kilowatt prototype is also developed using TMS2837D controller. Acknowledgements. Hardware is done at Jegathesan School of Engineering and Technology under AICT model of funding. These are the references. Thank you.